All right, so what we're going to do is the last three problems from the notes. And we're looking at an example from the book, number 53. The integral from 0 to x of 1 minus cosine t over t dt for all x. We want to express this integral as an infinite series. And notice one interesting thing about this is this function doesn't even exist, right, at 0. That is 0 is a discontinuity of that function, so that should look kind of weird. So let's first remind ourselves about cosine x, what that power series is. And again, you don't have to memorize these, but if you go down and look at this table, there's our power series for cosine. So I'm going to copy that again up next to our problem. So cosine x is the sum on n from 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. And now what we're going to want to do is we're going to want to find a power series for 1 minus cosine of t. All right, let's write out some of these terms. They look like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Notice it's an alternating series, and all the powers are even, and each one is divided by that same even number, factorial. So if I were to find 1 minus cosine t, notice I would take away the 1 would drop out. All right, and then I've got to put in the t's for all those, so that's t squared over 2 factorial, t to the 4th over 4 factorial, t to the 6th over 6 factorial, and this negative here would change all the signs. So that would become a positive t squared over 2 factorial minus t to the 4th over 4 factorial plus t to the 6th over 6 factorial. And if we wanted to divide those all by t, we should be able to get 1 minus cosine t over t is the sum on n from, let's see, let's start it at, bless you. The first one's going to be a positive. Then t squared divided by t, that's going to be t to the 1. But it will be over 2n factorial. So I'm going to call that t to the 2n minus 1, where n goes from 1 to infinity. Let's see, it'd be 2n minus 1. I wrote plus 1, and that needs to be minus 1. Let's make that adjustment. See if that works. Okay? So these were all even powers, but I'm going to divide by t. That subtracts 1 from those powers. So that becomes t to the 2n minus 1. And so now if we want to find that integral of that is the sum of the integrals. And if I write it this way, notice the negative 1 to the n over 2n factorial is just a constant in front, and I'm using the power rule here. And I'm going to integrate from 0 to x. So sum on n from 1 to infinity. That would be negative 1 to the n over 2n factorial. Power rule says add 1 to the power, so I'm back up to 2n, divide by the new power, and I've got to evaluate this from 0 to x. Got to evaluate that from 0 to x. Now, when I put the x in, I get sum on n from 1 to infinity, negative 1 to the n x to the 2n over 2n factorial times 2n. And what happens when I put the 0 in for all the t's? Right? 0 to any power is 0, right? And the first term, notice when I start with n equals 1, is not a constant. It's 0. And so this is my answer. So we did this with a combination of writing out the terms and then going back to sigma notation. And the key, one of the key parts was noticing that we changed this index because we did 1 minus. One of the terms dropped out. One term dropped out, and that's why we had to shift that. And the only reason this works at 0 is because we divided by the t here. When you divide by the t, we don't get anything over t. Okay? All of our terms, when divided by t, are still terms that are defined at t equals 0. All right. So I believe there's a couple problems in the WebAssign and on the review that you should try for that. Yeah, question. Yes, you can do it that way. You can. Sure. So this is the step that we're talking about right here. Okay. So when I divide through by t, it would be the same thing as dividing this by x, right? And so that reduces that power by 1 when you divide through by that. Yeah. Okay. So this would, the 2 would become 1, and then 3, and then 5, and so on. They become odd numbers, and that's where that t to the 2n minus 1 comes from. Yeah, question?
Wouldn't negative 1 to the n give you the first term that's negative?
Let's see here. Yes, it would. So we are going to have to adjust that, aren't we? You are right. How about if we put an n minus 1 on that? Thanks for paying attention on that. You are right. Thanks for that correction. Any other questions about that problem? Yeah. Yeah.
So if like 2 terms dropped out or something, would n equal 2?
Yes. If 2 terms dropped out, you'd shift it over again. Exactly right. Yeah. Yeah. Question.
Because you're taking the integral of that function.
Uh-huh.
Is that why the t to the 2n minus 1 becomes t to 2n?
Yes. Okay. So from here to here, that is the power rule, right? We're adding 1 to the power, dividing by the new power. Absolutely right. All right. Now, this says using a Maclaurin series, determine exactly what the value is for this series. So we're not going to estimate it. We want to know what that is. And in other words, we're going to have to compare to a series in the list. Well, it looks very similar to one we just did, right? We just said that cosine of x is the sum on n from 0 to infinity, negative 1 to the n, x to the 2n, over 2n factorial. And the only difference here is this would be cosine of pi, right? We've replaced all the x's with pi. All right, so it becomes a sort of a comparison, choosing the right series. And if you'll look for just a minute at the table, cosine has all the evens in the denominator. Sine has the odd factorials in the denominator. E has all the factorials in the denominator. So those should be pretty easy to identify. They're the only ones with factorials. The rest of these do not have factorials, and you can kind of take a look at those depending upon whether you're dividing by n or whether you're dividing by 2m plus 1. Whoops, I got to slide it up so you can see it. 2m plus 1 there. Okay. So it's just a matter of identifying the correct one that you need. So that one's cosine pi, and we know cosine pi is -1. Right. So if I were to write out the terms, that would converge to -1. Okay. All right, so this last one is for you engineering folks out there. Yay, right? Okay, question? Sure. Scroll back up so you can still see it. All right, so the last one is a really good example of how engineers might use Taylor series, okay, to write a function. And this one is voltage. When a voltage V is applied to a series circuit consisting of a resistor R and an inductor L, the current I at time t is given by this formula. So we want to expand I of t in a Maclaurin series and show that the current is very close to the voltage times T over L for small t. All right, so notice here is the Maclaurin part right here. So let's write out the sum for e to the x. Sum on n from 0 to infinity, x to the n over n factorial. And you don't have to memorize that, but of all the ones to memorize, this one would be the one. And so the next step we're going to have to do is find e to the -RT over L. And we should be getting pretty good at that. That's just substitution. We're replacing the x with -RT over L. All right, so let's see if we can simplify that. 1 minus e to the -RT over L would be 1 minus the sum on n from 0 to infinity, -1 to the n, r to the n, t to the n, over L to the n times n factorial. And we could start writing out some terms just like we did in the previous problem. And it starts off with the positive. All of these to the 0 power, that's just 1. Then we'd have minus RT over L times 1 factorial plus R squared T squared over L squared 2 factorial minus R cubed T cubed over L cubed times 3 factorial plus ... So we've got that combination of writing it using sigma and writing out the first few terms. And just like we had a minute ago, these drop out and this will change all the signs. All right, so let's put that I of t equals, let's go ahead and put V over R in front. So I'm going to put V over R. I'm going to drop out the ones and start changing the signs. So RT over L minus R squared T squared over L squared times 2 factorial plus R cubed T cubed over L cubed times 3 factorial minus ... And let's then multiply through by V over R. So let's see, that would be V, let me not do that, sorry. Let's just write out a few terms. The first term would be VT over L. The second term, let's see, we would have an RT squared over L squared 2 factorial times V. The next term would be VR squared t cubed over L cubed times 3 factorial. And notice if t is very small, these are approaching 0. The higher the power, the faster they approach 0. And so what that means is I of t, the current, is approximately the same as Vt over L if t is small. That's the most important term of all those when t is less than 1. When t is bigger than 1, we're interested in the highest power, right? But when t is smaller than 1, we're interested in the lowest power term. Okay? Questions? Maclaurin series. All right, great. So let's stop.